Bernoulli's principle is the reason airplanes fly, why curved balls curve, and a host of other physics phenomena. It is a little counterintuitive, though. It doesn't make sense until you dig into it just a little deeper. But here's a person holding and going to open a little window on the airplane here, and they're going to put their phone right up to the window, and they lose their phone. And that's due to Bernoulli's principle. We will explain. We have to understand that air pressure comes from molecules colliding against the surfaces. So if we had this in a container here, this surface, molecules are colliding into that. Some molecules are moving fast, some are moving slow. They're all going in different directions, but it's the cumulative force in a given area of all the different collisions at any given moment that creates the pressure that's on that overall surface. Now, we can look at that like the molecules inside of a balloon. The balloon is held open and stretching the rubber because the molecules are colliding against it and they're shooting over the other side and colliding against that as well. If you were to use what's called Boyle's law, that pressure times volume is a constant, this helps us understand that. Because if we were to take our hands and squeeze that balloon into a smaller volume, the molecules aren't going to change speed, but they are going to take less time to go across there. So they're going to be hitting the walls more frequently. Plus, those molecules are compressed into a smaller volume. So they're going to be hitting closer together on this wall. So if you take the volume and you decrease it by a half, there will be twice as much pressure inside that balloon. And again, we're looking at pressure in terms of molecules colliding against the surface. Well, we can do it on a macroscopic level and learn about billiard balls hitting the surface. So if I threw each of these billiard balls with the same speed and they all had the same mass, they would strike with the same momentum. And so that one hits there, this one hits there, that one hits there. And which do you think hits the surface with the least amount of force? And it is the blue ball. We can think of it in terms of impulse because this ball was traveling this direction and then it went in the complete opposite direction. So it had an impulse twice as much as if it had just hit and stopped and came to a stop. This ball was traveling mostly to the left, so its momentum didn't change in that direction. It just changed a little bit as a little bit came in and bounced and a little bit came back out. So this ball had the biggest change in momentum, the largest impulse, and this one had the least. And this is going to put the least amount of force on that surface. If it really takes a demonstration to wrap your brain around that, consider yourself in a billiard ball thrown square or glancing off your forehead here, or one thrown square against hitting just perfectly into your forehead. Yeah, that's going to hurt. This is only going to glance off, not hurt nearly as much. The hail damage on this car also demonstrates that. There's a lot of hail damage up here, not so much hail damage down there. And we can look at the contour of the surface. We're assuming that the hail was dropping vertically onto this surface. And this is the angle of the surface, and that's where the hail hit. This was less of an angle, and this hit almost squarely on. So when the hail hit squarely onto the surface there, it did a lot of damage, put a lot of force on that surface. We can think of it in terms of vectors, and that if this is the momentum of the object coming in, and this has had the same momentum but at a little bit different angle, we'd have to find the component of the momentum that was perpendicular to the surface. And if it hits at a very big angle, there's only a tiny component that is into that surface. So as I was saying again before with impulse, if this had momentum this way and bounced straight back that way, the change in momentum was twice that. But if it came in this way and bounced off that way, the impulse was twice that. And if it came at a very big angle and came in like this and bounced off at the same angle over there, the impulse would only be twice that. And you may be familiar with Francesco Bernoulli from Cars. Well, this is not, he didn't come up with this principle, but his older brother, Daniel Bernoulli, came up with this idea. And it's called Bernoulli's Principle. And it says the faster a fluid moves across a surface, the less pressure it causes on the surface. We have to connect with that. The faster a fluid moves across the surface, the less pressure it causes on the surface. So Bernoulli's principle deals with air flowing across parallel to a surface. And a Newtonian force would be air flowing against or perpendicular to the surface. So it's very reasonable to assume or to connect with and make sense that the faster this air flows against the surface, the more pressure that air is going to put on that surface. That makes a lot of sense. What might be a little counterintuitive is that when you blow air across the surface, the faster that air blows, the less pressure that air puts on that surface. And we can make sense of it because if air is blowing against it, it has a component perpendicular to it, but the faster that air flows, the more it is at a diagonal or a glancing type blow. The molecules just glance off that surface versus hitting squarely against it. So if you take two aluminum cans here and blow air between the two, you might think that that air would push those two cans apart from each other. And if you think that, you're thinking in terms of Newtonian forces. The air struck it and pushed it away. But Bernoulli's principle wins out here. The faster the air blows across the surfaces there, the less pressure it puts on those surfaces. And the atmospheric pressure, the molecules colliding against this side, are hitting more squarely against that surface, where the air that is hitting in between only hits at more of a glancing type blow and puts less pressure. It would actually make those two cans come together. If you take a funnel and a ping pong ball and blow air down this, you might expect the ball to be pushed down. And again, you would be thinking about Newtonian forces, that the air struck it and pushed it away. And it does. But the stronger force is the Bernoulli force, is that the air is flowing over the top of that. And because that funnel redirects and causes the air to flow over that surface, the faster it flows, the less pressure, and the atmospheric pressure is holding it up. The molecules of air down here are colliding squarely against it, and the molecules that are flying past here are only hitting at a glancing type blow. You could do this yourself with just a straw and a piece of paper glued or hot glued to it, and then a larger piece of paper. Usually you need to put a pin through it so that when you put these two things together and blow air through it, the pin just prevents it from sliding around. But these two pieces of paper are kind of layered together, so it redirects and makes the air flow over that top surface. And again, the faster the fluid moves across that surface, the less pressure it puts on that upper surface. The atmospheric pressure underneath is holding it up. And you may have noticed this if you have a shower curtain like this vinyl one here, where if you have cold water in the shower, not much happens, but if you have hot water, all sorts of steam is rising up, and steam is a fluid. By the way, Bernoulli's principle does not just refer to air, it's liquids and gases alike. It refers to fluids. But as that steam flows up here, you might have noticed the whole shower curtain pulling in away from that. To get away from that, they put these little magnets or weights on the tips of the curtain to help it hold against the side of the tub. If you had a house like this and the wind blows across that house, the faster the wind blows, the less pressure there is on the roof. The air in the attic up there is more stationary, and the wind could blow fast enough so that the pressure above the roof was a lot less than the pressure under the roof, and it could blow the roof off, like in this tornado here. Here's the roof, the air is blowing across, and it just low pressure pulled it straight up. Maybe your grandmother, or you don't see these too often anymore, but they're a perfume atomizer, where you squeeze this bulb and air blows across this and it puts out a little spritz of perfume. Maybe you've seen it in a garden where you push this thing and you can spray pesticides or other things onto the plants, maybe fertilizer. But this straw goes down into the fluid here, and when you push this thing, it blows air across the top of that. And blowing air across the top of that lowers the pressure up there. There's a hole here that allows the atmospheric pressure to push on this surface. So the pressure inside that tube drops by blowing air across. The atmosphere pushes that up, and then Newtonian forces take over and collide into that and push it away. That's what an airbrush does. There's a little air pump, and it blows air across a straw that goes down into the paint, and you can blow paint out like this. Or a pressure washer that uses soap. There is an attachment where the water's flowing through here. This goes down into a reservoir of soap, and as the water flows through here, lessens the pressure inside there. The soap is drawn up, mixes with the water, and shoots out like that. Some of these plastic tubes you can fill up with air and wave them around as these people are doing, but you could blow them up with air, kind of like you're blowing up a paper bag where you put it in your hand and then blow air right into it, but only the air from your lungs fill that up, and it may take 10, 15 breaths of air to fill that up. But if you hold your mouth back away from this and blow air across it, that fast-moving air creates a low pressure area where it's moving fast. And that higher pressure where the air is not moving fast, air travels from high pressure to low pressure. So not only is your breath going to go into there, it's going to recruit other air to join it, and you can actually fill up that whole bag in one breath of air. A little air nozzle for blowing off the dust on your workbench or something. But if you notice, there's that hole, a little nozzle there. Air comes out right there and blows very fast through there, but that fast-moving air lessens the pressure inside there, and the air from the outside joins in, and you can get a lot more air flowing through there than just the air that was coming out of that hole. The escape slide on an airplane, there's a little, I have a scuba tank here, but it's a similar idea, that the air inside this tank is not enough air to fill up that whole escape slide. So it's essentially just this nozzle that's held back away. Air flows really fast, lowers the pressure where it's flowing fast, and this air out here joins in and fills it up as well. And I did say earlier that this refers to Bernoulli's principle as fluids, both liquids and gases. So if I had a ping pong ball on a string here, and I hold it in that stream, that water flowing across the surface there lessens the pressure on that side. And the atmosphere hitting on this side holds it in. And that might be mind-boggling, totally counterintuitive. And again, if you think that is true, you're only thinking of the Newtonian forces. The water striking that surface should be pushing it away, but the water flowing over that surface lessens the pressure. Atmospheric pressure is holding it in. And there it is again. All right. A Venturi tube is just, you got to get all that water through that constriction. So however fast the water's flowing here, it's got to be flowing faster through that narrowing to create the same flow. But if it's going faster here, the cross-sectional area went from big to smaller. It's got to go some speed here and speed up in through there. That increased speed drops the pressure in there, and that's Bernoulli's principle. The faster it flows, the lower the pressure. You can take like a shop vac and the nozzle and a ping pong ball and blow air up like this. The air striking the bottom of this ping pong ball is what's holding it up. Gravity's pulling it down, but Newtonian forces are holding it up. But the ball will bounce back and forth like that. And the reason is, if the ball got a little too far to the left, this side of the ball is in fairly stationary air, and the air is flowing over that side. So if it got too far to the left, there's going to be more pressure on the left, less pressure on the right, and it's going to pull it back into the stream. If it overshoots and goes off to that side, well, the same thing but opposite would happen. This shape here is called an airfoil. It's the shape of an airplane wing, and it has a bigger curvature on the top, more flat on the bottom. And if we had two little air molecules just sitting there minding their business, and this plane rudely separates the two, one goes up, comes back down, this goes down, comes back up, but it's the same difference as if the plane wing were stationary and the molecules were flying past it. One way to think about this is that this is the path the upper molecule followed, and it went a greater distance in the same amount of time. So one way to think about it is that it had to have been traveling faster over the top because it went more distance in the same amount of time. And the air flowing faster over the top creates less pressure, and the atmospheric pressure holds that wing up like this. Now remember, atmospheric pressure at sea level is about 14.7 pounds per square inch. As that plane is flying through the air, it's going to decrease the pressure both on the bottom and the top because the air is flowing over it. But the pressure dropped more on the top because it was flowing even faster. And in this example, there's a difference in pressure of about 1.3 pounds per square inch. And that doesn't sound like a lot, but if you have a lot of square inches, like this airplane wing here, it's a shape of a trapezoid. And these are the dimensions given by Boeing. It's a trapezoid, so average of the bases times the height. This is the weight of the airplane, and we plug in the dimensions given there, and we find that it's about 2,407 square feet, but there's 144 square inches in a square foot, so we get this many square inches. And if there was a 1.3 pounds of force difference for each square inches, you get this many pounds of lift on just one wing. A little difference in pressure over a lot of area can make a big difference. The angle that the wind is striking is called the angle of attack. So if the air hits like this, there is a component that's perpendicular to, there is a component that's parallel to. So this component is going to create the Bernoulli effect. This component would be a Newtonian force striking that wing. The Newtonian force has a component back and a component up. So there are Newtonian forces that do lift up that thing, but it also has a component holding it back, and that component is called drag. You want to minimize the drag just so it's efficient. The flaps on a plane extend down like this when it's landing. So two things that it does is a plane can fly 500 miles per hour, but you don't want to land going 500 miles per hour. And so you need to travel slower, you get less lift. So that increased surface area creates more lift because it's a difference in pressure over a bigger area. And then it's angled down like this to get some Newtonian lift as well. And that also causes drag, which slows the airplane down. This is a neat video from Cambridge University using smoke trails to show air going over that surface. And when we see the pulsed air, it really shows that the air did go faster over the top. So They all start out together, but when it hits that wing, this one slows down, and that air did travel faster. And it does push the air down, and as it flies, this is an airplane flying through the smoke, pushes the smoke down, smoke pushes the airplane up, and all is good. With sailing, there's different types of sails. This would be the main sail. This sail that comes out in front is only used when the sailboat is in a run, which is going straight down, downwind in the same direction as the wind. But that sail is called the spinnaker. And you can imagine what type of forces the spinnaker uses. It's Newtonian forces. It's blowing air against it. Now think back to relative motion, that if the boat is traveling 10 knots and the wind is blowing 10 knots, well, there's no wind relative to the boat. So that couldn't happen. And it turns out that Newtonian forces are not the primary forces that make sailboats go. If you look at the flag on this sailboat here, you can see the apparent direction of the wind. The apparent direction is the combination of the actual direction of the wind combined with the direction the boat is traveling. But from that, you can see the wind is blowing across these sails, not against the sails. So sailboats use Bernoulli forces. And on the sails, we put these little ribbons, green for the starboard side, red for the port side, and we want to be able to look at those and see that the wind is blowing very smoothly across those sails. And if they don't, you can trim the sails to, if this one was limp and hang straight, you'd pull the sail in a little bit to get more wind flowing and to increase the Bernoulli effect. And so this is a sail that you can see the curvature of that, and it just low pressure on that side pulls it on along. You could use a rigid sail, and this is a sailboat that went 62 miles per hour, and that's impressive. This is a rigid sail for land, and that car went 126 miles per hour, and that is very impressive, but just using wind. The umbrella here is the shape of an airfoil, and you got to be careful because as the wind blows across that, it can lift up, lowering the pressure and make you fly away. In all these upcoming examples, I'm going to refer to how you can put spin on a ball and make it curve. In all these sports, putting a spin will make it curve. Let's see if we can understand that. A neat shot here with a penalty shot for soccer. Boy, did that ball curve, even fooled the camera person. So if we have a merry-go-round and it's going around with a tangential velocity of 10 miles per hour, the top is going 10 miles per hour that way, bottom's going 10 miles per hour that way. But if there is wind blowing and the wind is blowing 15 miles per hour that way, these cars are passing the wind at a relative velocity of 25 miles per hour. And here, because they're going the same direction, the wind overtakes and only passes at 5 miles per hour. So at the top, well, I got ahead of myself. If you put the whole Ferris wheel on this train here and went that way at the to the left at 15 miles per hour and the wind was not moving, well, it'd be the same effect, just relative motion. And on the top, indicating that you're going to get a lot of wind in your face, and at the bottom, not much wind in your face. So do that with a baseball. If the ball is moving to the left and it's rotating like that, it's called topspin. So the top is going to have a lot of wind blowing across that surface and not much wind blowing across that surface. So here is air that's stationary, and if the ball is not spinning, the air is flowing over each surface the same. But if you put topspin, it's flowing over that surface faster than the bottom surface, and the faster means less pressure, Bernoulli's principle, which is going to make that ball go up. Any questions? Well, I hope you have a question, because I just explained the exact opposite of what actually happens. If you've played sports, you know that topspin makes the ball go down, not up. So let's see if we can bring in more variables here that will help us actually understand. Just like when Earth rotates, there is air that is trapped against the surface of the Earth that rotates with it. So if the ball is rough, it's going to kind of capture air with it, and it will rotate with it. So as it's going along like this, the air that's going with it collides into the air that's coming from this. The air that's coming around collides into the air that's going that way, and that head-on collision slows the air down. On this side, the air is going in the same direction, so it doesn't have that head-on collision and it doesn't get slowed down. So if it doesn't get slowed down, it's going faster on the bottom, less pressure, and it gets pulled down. And I did say that if the ball is rough, it will trap more air with it. So sometimes pitchers will take an emery board or sandpaper and roughen up the ball. It's illegal and not a good thing to do for the sport. Tennis balls spin really well or are very fuzzy, and when they spin, they curve a lot. Racquetballs, they don't curve a lot because they're not nearly as fuzzy, doesn't trap air against the surface. But if this ball is moving to the right and spinning this way, another way of thinking about this is with what is called the Magnus force, that the air is going to get trapped and get pulled up along the bottom. The air that hit there just slowed down. And so essentially the ball pulls the molecules up. Newton's third law says the molecules are going to pull the ball down. And we can see that this is spinning. When it's spinning, these smoke trails are being pulled up. So ball is pulling the air up and air is pulling the ball down. You can use this in like airsoft or paintball. If you put a spin on the thing, backspin this time, it will create a force that is lower pressure on the top of the ball. And the ball curves out like this with backspin and helps make the ball on a more straight trajectory. Helicopters flying through the air like this, the blade's going around. This blade is going against the direction of the wind. This blade is going with the direction of the wind. So air is actually flowing over this surface of the blades faster than this surface. And that's creating more lift on this side than that side. Now the pilot can change the pitch of these blades every half turn and compensate to make the flight stable. But that creates a limit, a speed limit for the helicopter, that there's a limit to how much you can compensate the pitch to reduce the extra lift here. And if a helicopter is going to go really super fast, you don't want one side getting more lift than the other. So if a helicopter is going to be able to break records and go faster and faster and faster, you really need two blades going in opposite directions so that that effect gets canceled. And then a boomerang is very much like an airplane wing. It's shaved down here and shaved down here. So as this thing spins through the air like this, it's going that way and spinning this direction. This side is cutting against the air. This side is fleeing away from the air. But air is going to be moving over that side faster than this side, and it's going to create more lift on that side. So what happens is, looking at this boomerang like this side was cutting into the air, this side was fleeing from the air. This is going to get more lift than that. That's always going to be perpendicular to its motion, and it's going to put it into a curved path. And it's Bernoulli's principle that makes boomerangs come back. And I think we will end there with a nice picture of a boomerang with maybe a 4th of July sparkler on it.